Welcome everyone. Today, we'll explore how acidity, measured by pH, affects material durability and its relationship to corrosion in the chemical industry. This topic is crucial for ensuring safety and efficiency in industrial operations. Corrosion is a major concern in chemical plants. In this session, we'll define corrosion, explain why it matters, and discuss the role of pH in influencing corrosion behavior. Corrosion is a critical issue in the chemical industry because it directly impacts equipment integrity, operational safety, and economic efficiency. Corrosion leads to material degradation, which can cause leaks, contamination, and catastrophic failures in pipelines, reactors, and storage tanks. The chemical industry often deals with aggressive environments involving acids, bases, and salts, making corrosion control essential. Understanding the relationship between pH and corrosion is vital because pH influences the electrochemical reactions that govern corrosion processes. By managing pH levels, industries can minimize corrosion rates, extend equipment life, and reduce maintenance costs. This introduction sets the stage for exploring how pH interacts with different materials and why it is a key parameter in corrosion prevention strategies. pH is a measure of the hydrogen ion concentration in a solution, indicating its acidity or alkalinity. The pH scale ranges from 0 to 14, with values below 7 considered acidic, above 7 alkaline, and 7 neutral. In the chemical industry, pH is a fundamental parameter because it affects chemical reactions, solubility, and corrosion behavior. Acidic environments, low pH, typically accelerate metal dissolution, while alkaline conditions, high pH, can either protect metals through passivation or cause localized corrosion such as pitting. Monitoring and controlling pH is therefore essential for maintaining process stability and preventing equipment damage. Understanding pH helps engineers predict corrosion tendencies and implement effective mitigation strategies. Electrochemical basis of corrosion, impact of pH on different materials. Corrosion is fundamentally an electrochemical process involving anodic and cathodic reactions. At the anode, metal atoms lose electrons and dissolve into the environment, while at the cathode, reduction reactions occur, often involving hydrogen or oxygen. The pH of the environment influences these reactions by altering the availability of hydrogen ions and hydroxide ions. In acidic conditions, high hydrogen ion concentration accelerates cathodic reactions, increasing corrosion rates. Conversely, in alkaline conditions, hydroxide ions can promote the formation of protective oxide films on metal surfaces, reducing corrosion. However, extreme alkalinity may lead to localized attacks such as pitting or stress corrosion cracking. Understanding these mechanisms helps engineers design effective corrosion control strategies. Different materials respond uniquely to pH variations. For example, carbon steel corrodes rapidly in acidic environments due to active dissolution, while stainless steel may resist corrosion through passivation in mildly alkaline conditions. Aluminum forms a protective oxide layer at neutral to slightly alkaline pH but suffers severe attack in highly acidic or highly alkaline environments. Copper alloys generally perform well in neutral conditions but can experience accelerated corrosion in acidic solutions. These material-specific behaviors underscore the importance of selecting appropriate materials based on the expected pH range in chemical processes. Engineers must consider both the operating environment and potential pH fluctuations to ensure long-term equipment reliability. pH control in industrial processes, material selection, and protective measures. Maintaining optimal pH levels in chemical processes is a primary strategy for controlling corrosion. Industries use buffering agents, neutralization techniques, and automated pH monitoring systems to stabilize pH within safe ranges. For example, in cooling water systems, pH is adjusted to prevent scaling and corrosion simultaneously. In acid pickling operations, inhibitors are added to reduce metal attack at low pH. Continuous monitoring with sensors ensures that deviations are corrected promptly, minimizing corrosion risks. These practices not only protect equipment but also enhance process efficiency and product quality. Effective pH control is therefore a cornerstone of corrosion management in the chemical industry. Selecting materials compatible with the expected pH environment is crucial for minimizing corrosion. Stainless steels, nickel alloys, and titanium are often chosen for acidic or alkaline conditions due to their superior resistance. Protective coatings, such as epoxy or polymer linings, provide additional barriers against corrosive media. Cathodic protection systems can also be employed to counteract electrochemical reactions. Combining these measures with pH control creates a comprehensive corrosion prevention strategy. Engineers must evaluate cost, performance, and maintenance requirements when implementing these solutions to ensure long-term reliability and safety in chemical plants. Corrosion failures due to pH imbalance, successful pH management strategies. Poor pH control can lead to costly failures. Acidic condensate caused severe pipeline corrosion, while alkaline cleaning solutions led to stress corrosion cracking in stainless steel tanks. These examples highlight the need for continuous monitoring and proactive maintenance. Several real-world cases highlight the consequences of poor pH control. In one instance, a chemical plant experienced severe pipeline corrosion due to acidic condensate, leading to costly shutdowns and repairs. Another example involves storage tanks where alkaline cleaning solutions caused stress corrosion cracking in stainless steel components. These failures underscore the importance of continuous pH monitoring and proactive maintenance. Learning from such incidents helps industries refine their corrosion management practices and avoid similar costly mistakes. Companies that implement robust pH control programs report significant reductions in corrosion-related failures. For example, a petrochemical facility introduced automated pH adjustment systems in its cooling circuits, resulting in extended equipment life and reduced maintenance costs. Another plant adopted advanced coatings and material upgrades alongside pH stabilization, achieving improved reliability and safety. These success stories demonstrate that proactive pH management is not only technically effective but also economically beneficial, reinforcing its role as a best practice in the chemical industry. Summary of pH corrosion relationship, future outlook and recommendations. The relationship between pH and corrosion is fundamental in chemical industry operations. Acidic environments accelerate corrosion, while alkaline conditions can either protect or damage materials depending on their properties. Effective pH control, combined with appropriate material selection and protective measures, is essential for minimizing corrosion risks. By understanding these principles, engineers can design safer, more efficient processes and extend the lifespan of critical equipment. Looking ahead, advancements in real-time pH monitoring, predictive analytics, and smart coatings will further enhance corrosion control strategies. Industries should invest in training, technology, and research to stay ahead of corrosion challenges. Continuous improvement in pH management practices will not only reduce operational costs but also improve safety and sustainability in chemical manufacturing environments.